Last time, we introduced the definition of weak derivative of a function. It agrees when we have a smooth function. Now, we are going to look at spaces function using these weak derivatives that contains all C0 finite element spaces. The idea is we want to take the limit of a finite element approximation as the triangular mesh getting smaller and smaller, which is h goes to 0. We want to see if we can show that it converges to the exact solution of the problem as h goes to 0. In this topic, Sobolev spaces, we are now in a position to define a space that contains all C0 finite element spaces. This means that we can consider the limit of finite element approximations as h goes to 0. Definition 7, the Sobolev space H1. H1 omega is the function space defined by H1 omega equal to u in L1 log, where the norm of u is less than infinity. Let's talk about norms H1, H2, H3, and so on. Now, we can continue define spaces of functions. The H1 space is the space function whose H1 norm is a finite number. So the H1 norm is well defined. If you want to go to higher derivatives, higher weak derivatives, then we can just define Hk to be the space with function with the finite Hk norm. And this function space H1, H2, H3, Hk are called as Sobolev's space. We use the fact that L2 and this pattern continues for Hk and Hl for k less than L, so the space contained on each other. Hk is contained within Hl for k less than L. If we are to consider limits of finite element functions in these Sobolev spaces, then it is important that they are closed, which is limits remain in the space. The whole point that we're going to consider the limit of a finite element function as the triangular mesh gets smaller and smaller. We want to note that if we do that, then we'll get something still in the Sobolev space. The space Hk is closed and the proof is given here. Theorem 10, H equal to W. In this theorem, it unifies two definitions of spaces. Let omega be any open set, then Hk omega intersect with C infinity is dense in Hk omega. The interpretation is that for any function u in Hk, we can find a sequence of C infinity functions ui converging to u. This is very useful as we can compute many things using C infinity functions and take the limit. What it means that any function in Hk can be approximated arbitrarily closely by C infinity function. Theorem 11, Sobolev's inequality. Let omega be an n-dimensional domain with Lipschitz boundary, let k be an integer with k greater than n over 2, then there exists a constant c such that L infinity norm of u, taking the sub, and it has an upper bound c u h k. Further, there is a C0 continuous functions in the L infinity equivalence class of U. If this condition hold, then the statement U L infinity equal to the sub of U x within omega is less than C, a constant C, times the norm of U of hk omega. Previously, we saw this result for continuous functions. Here, it is presented for hk functions with an extra statement about the existence of C0 function in the equivalent class. The interpretation is that if U in hk, then there is a continuous function U0 such that the set of points where U is not equal to U0 has a zero area or volume. In the next corollary, Sobolov's inequality for derivatives. Let omega be an n-dimensional domain with Lipschitz boundary. Let k be an integer with k minus m greater than n over 2. Then there exists a constant c such that the statement is provided here. Further, there is a Cm continuous functions in the L infinity equivalent class of U.